Greetings, this is Mr. Garwood with our continuing video series on Calculus 2nd edition by Briggs, Cochrane, and Gillette. This video is going to focus on setting up the idea of what a derivative is and what it means. We're going to start here with, I just have a coordinate grid laid out, and we're going to look at the idea of if I have some function moving through this thing, what is the derivative and what does it tell me? Now, in algebra, in high school algebra, we talk about the idea of an average rate of change over an interval. So the idea is you have some starting value, which for our purposes we'll call the point C. And then we have an ending value we'll call that point D. And we can talk about the average rate of change, which is the slope of the line that connects those 2 points. Now, we'll call this slope CD. Now, the idea here is that you have in the x-coordinate direction, you have some change in x. And we denote the change in x with a delta x. This is the Greek letter delta. And similarly, we also have a change in the y direction. So this output would be f sub c, where we'll say that this function is some function f of x, and so too does the d coordinate have an output f sub d. So just as we have this change in the x, we also have here a change in the y direction. So we can actually say that the slope of this line from C to D is the change in y over the change in x. And you may remember someone saying this is rise over run, and there are a whole lot of other ways to express that. But the change in y is simply the y coordinate for this point, so f sub d, minus the y coordinate of the original point, so that's f sub c, and that's over the change in x, d minus c. So this distance is d minus c, and this distance is f sub d minus f sub c. And notice I'm keeping these in order, greatest x to least x, greatest, and then greatest x to least x here as well. Now that's all well and good, and that's usually where your college algebra and your pre-calc classes ended off. The question though is, this tells me the average rate of change from C to D. What if I'm not interested in an average rate of change? What if I'm interested in what we term a instantaneous rate of change at C? So what I mean by that is, if I draw a tangent line, so this is tangent to the function, which means it only crosses once here, and it only crosses when x is c, and its slope is such that it perfectly touches that point, and it's behaving similar to that function in that frame. Now, there's a couple things I want to note. So we're going to call this slope tangent line. Number one, it exists. I think it's obvious here. We can see there is a tangent line here in green. It exists. Number two, it has slope. It's not undefined. It's clearly not a perfectly vertical line. The question today is how do we find that? And this is where our understanding of calculus actually begins, is this idea of how can I figure out this green line? How can I figure out its slope? And not just by, if we had a coordinate grid, maybe we could go in, find some points and find the slope of it. But how can we do this regularly, just like we did this calculation? Now, one thought is, well, what if I just treat C as one point? Because I have the point here, C, S of C. Well, that would mean that the slope of the tangent line is F of C minus F of C over C minus C. Well, obviously here, that's 0 over 0. Bad math. Because I'm dividing by 0, everything's bad, everything's broken. This clearly does not have any kind of infinite slope. We said just a moment ago, it has slope. So how can we figure out what that is? One way, and this is a slightly different viewpoint of this, we're going to say this line in red represents the tangent line. And what I have done is we've created several points where we keep bringing the secant line, that line that goes through 2 points, where we talked about average rate of change. And once again, here we have our change in x, and that's expressed by this, and our change in y here. The question here is, if we notice as my delta x gets smaller, as these points get closer and closer to this original point, what is happening to those slopes? What I'm hoping you notice is as the x-coordinate where I'm intersecting comes in, these slopes are getting closer and closer and closer and closer to this tangent line. And so the question then becomes, how can I evaluate this convergence? And what I'm hoping you see is that if we take all of these in turn, well, I'm really just taking a limit as that delta x gets smaller. So going back to this original sketch we started with, and I've got some function doing something. I'm interested here in this value C, and it has y-coordinate f of C. What I'm going to do is I'm going to pick an arbitrary point, and what I mean by an arbitrary point is I could pick any point anywhere else on this graph, and I'm going to be really original. I'm going to call it x. And where it crosses the y, or its y coordinate as f of x. And the point I want you to see is, as x gets really close to C, this line so for this initial x I drew, that's it. And we're going to say that the actual tangent line, I'm going to draw it in green here. Well, if I pick another x that's a little bit closer, so let's say it's here instead. And then maybe one again still. These lines get closer and closer and closer to this green line, which is our tangent line. So, there are actually two definitions of the derivative. The first one I'm going to give you is this. Number one, focusing here on the change in x is x minus c. which also means here the change in y is f of x minus f of c, then we're going to say the limit as x goes to c, so we talked about how x is drawing closer and closer to c, of f of x minus f of c over x minus c. So, definition of the derivative. Now, what I really want to focus on over here is, hey look, delta y, delta x is f of x minus f of c over x minus c. So what I'm doing here is I'm taking this traditional slope formula, and I'm applying it with a limit where this value of x is getting impossibly close to c. And by evaluating this, by taking that limit, that gives me the slope of the tangent line. And you'll notice here, if x is c, if we go back to thinking about taking the limit of rational functions, this would give me a denominator of 0. So I go back to, the idea is we're going to have to end up canceling something out, and we're going to pick that up in our next video where I talk about evaluating derivatives using this process. I hope you found this video useful, and good luck in the coming semester.